Okay. Okay, so I'm Marco Minici, PhD student at University of Pisa and CNR. Uh, Also, this work is a joint work of CNR, Gentai, University of Pisa, and Sapienza University. And yeah, we will talk about an echo chamber detection algorithm based on a probabilistic framework that exploits information cascades. Okay. First of all, an outline of the presentation. We will have an introduction where we will introduce the problem and why it is relevant. Then also some motivations that they are more related to the intuition underlying our ideas. And then I will describe the framework, show you the results of our experimentations, and there will be also a brief discussion of the outcomes and the limitations. Okay, introduction. What is the basic functioning of echo chambers? What are echo chambers? Here I report a toy example where we have a social network and each user stands for either the red side or the blue side, and the two sides can be whatever topic related to whatever topic, for instance, conservative against liberal, or pro-vaccination against vaccination. And what can happen is that one user can post some piece of content, I don't know, like saying COVID vaccine causes genetic mutations, and then this tweet, for instance, can be retweeted from one of his neighbor, and then another neighbor retweets it and disclose, let's say, the triplet, and the original poster can see either its own content or another content which is very similar to the one he posted originally, and this acts as an echo, and it triggers some cognitive biases of that we have as human beings. Here I report 3 examples. We have the problem of confirmation bias. Human beings tend to believe to information that confirms his pre-existing beliefs. And then we have also a problem of herding bias, because of course the social network, in this way, we tend to think that the majority of people think the same of us, and this can be, of course, a problem. And also we have a problem of exposure bias, because this kind of network structure can hinder the, let's say, the propagation of the opposite side. So we have no chance. We are only exposed to the same content, and we really don't have any chance to form a different opinion. And from this fact, in the literature, echo chamber detection is approached as a modularity maximization problem. Basically, we have a network, and we try to find the communities that are well isolated from the rest of the network. So we apply community detection algorithm, and then on the top, we apply a content information analysis step, where we analyze which kind of content each user in the community is sharing. And so in this way, we can label the community as a echo chamber or not, for instance. But this is a kind of artificial construct, and in the sense, we are really not using the problem. We are really solving the problem of echo chamber detection without applying the proper definition of echo chamber, because the echo chamber is where partisan information propagates, and not necessarily part of the social network that are modular, let's say. And so we want to fill this gap, and we start from a very inspirational quote from Kleinberg in his book Networks, Crowds, and Markets. Basically, we think that cascades and clusters are really, there is a really a deep entanglement between the two. And we are able to explain the clusters in accordance to how the cascades of information propagates in the network. And we want to use these, let's say, this information, this quote, and extend it to the echo chamber realm. And so we start from this idea of echo chambers as clusters that lets partisan content propagate. And we want to investigate an algorithm which is able to implement this definition. So yeah, we proceed with the framework. We have a set of observables, so let's say a set of data that we are able to gather from the social network. We have the social graph, which is a directed graph. Then we have a set of items, and each item is labeled with a polarity between -1 and 1, where the sign tells you the side of the topic, and the absolute value tells you the magnitude of let's say of how much it is aligned with one of the two topics. And then we have the cascades for each item. Basically, it is the set of users that activated on that item, that propagated that item. We defined a set of latent variables through which we want to explain the observables. First of all, we have the vector, the polarity vector of the communities. Basically, for each community, we have a scalar value between -1 and 1, and the absolute value tells you the more higher is the absolute value, the more the community is an ideal echo chamber, and then the sign tells you the alignment. And then we also have two matrices, phi and theta, that represents the engagement of each user to each community from 2 points of views: the social engagement and the polarized engagement. In this diagram, we have there is a summary of these two variables. On the left, we have phi, and phi is able to partition the set of users in social communities. So only considering the social links, let's say, that we observe. While on the right, theta helps us to establish a set of communities with respect to the content, with respect to the information. So we are also able to attach a color to the community. Okay, we model the cascades in the following way. We define, given the cascade was generated by a given community C, the likelihood of a given cascade is a combination of two factors. The first one is whether the item polarity is aligned with the community polarity. If the two have opposite signs, the likelihood is 0. We don't let different items to be propagated inside a community of a different polarity. And then we need the user involved in the cascade to be engaged from a polarized point of view in the community. So they must be, let's say, interested in the topic of the information that propagates inside the community. For the links, it's similar in the sense that, again, here we have a convex summation, and the first part is basically a Bernoulli trial. We toss a coin using the absolute value of the polarity of the community, and so if it is an echo chamber, users are extracted using the value of theta, of the thetas. Otherwise, if it is a social community, we use the values of phi to extract the users from the population. And in the end, we can learn our latent variables, theta, and phi, by maximizing the likelihood of observing all the links and all the cascades in our training set. Of course, this is not easy, and we resort to an expectation maximization iterative algorithm to find the optimum solution. And first of all, we perform the expectation step, where we estimate this quantity y of which is the latent community assignment of a link, as you see on the left, and of a propagation, as you see on the right. And in the end, we compute the likelihood Q of the likelihood of our links and of a batch of links and cascades, and we compute this basically becomes a training loss, and we perform backpropagation using stochastic gradient descent to find an optimum solution. Okay, here we show the results by applying, first of all, our model to 3 different real-world datasets. They are extracted from Twitter, and they are related to 3 different polarized debates. The first is Brexit. The second one is the Italian constitutional referendum, and in the end, the vaccine, anti-vaccine debate. And basically, we wanted to use a metric that is used in the literature. So each community is evaluated in accordance to its conductance and its purity. The conductance is how easy it is to isolate each community from the rest of the network, while the purity is the proportion of like-minded people inside the community. And we obtain all the polarized communities that we obtain are both have low conductance and high purity. And it's really interesting because we really do not explicitly maximize for conductance, at the contrary of the literature. But we also obtain interesting results in this sense. And also we can see on the right, with the Vax-Novax dataset, that we obtain 2 communities, 2 social neutral communities, the one yellow colored. And one community is a community that acts as a bridge. It is between the 2 communities, and it contains the news outlets. Of course, we could say that the news outlets could be polarized, aligned in a sense, but as we can see, they act as as a bridge between the 2 communities, and our method is able to discern this difference. And then the other community is a community of users that do not activate a lot. They have only like 2-3 activations, and so in this sense, our method is able to grasp a notion of uncertainty. It's not able to be sure, it's not sure whether to put these users in a polarized community, so it creates this social community. And yeah. Then what we have done also is using our estimated latent variables to solve a set of downstream tasks. We begin with a stance detection task. Stance detection is the problem of giving a user understand whether it is aligned with one side or the other one. And we saw that on the 3 datasets we obtain really good results, and we are only beaten by 1 baseline, not-2-vec plus logistic regression, only in the case of the vaccine dataset. And the second downstream task is the next activation prediction problem. When we have an information cascade, we could be interested in guessing who is the next user in the network who is going to retweet that piece of content. So what we do is taking our training dataset and masking part of the information cascade, and then testing whether with our latent variables we are able to predict the masked users. And we see that we obtain good results. Only in the case of the vaccine dataset we obtain better results only until the 10% of masked activations, but then the performances degrade gracefully. So we could say also that our model is kind of resilient to missing data, because of course having 30% of masked activations can be, of course, introduce some noise in the estimation. And yeah, in the end of the discussion, we can talk about the limitations of our work, of course. First of all, we are using a stochastic gradient descent plus variational inference techniques, and we know that we will not obtain a global optimum solution. And so the question is, there can be multiple minimas, local minimas. How different local minimas are different from each other? And can this impact the final result? I mean, providing substantially different communities. We did not explore this problem, but I think that this can be a limitation of our work, and better understanding this aspect is significant, is important. And then also the fact that we consider one topic at a time. We know that a user on social media is not, users on social media talk about everything, not only about a single topic. So to really give a comprehensive characterization of the users and therefore of the echo chambers, we should take into account more than a topic. And I think that this also relates to the, let's say, trying to better define the phenomenon of echo chambers. And this is a challenge for, let's say, this research topic, this research line. And then the conclusions. We provided the first model-based approach for echo chamber detection. And also, by checking the fact that our model is able to correctly fit real data, we are kind of confirming the assumptions at the base of our model. So we are confirming that there is a deep entanglement between content spreading and community memberships. And also we proved that our model is able to extract latent variables which are informative not only with respect to the community detection problem, but also to other tasks. And this is final wrap up. So we talked about this probabilistic framework to detect echo chambers. And as future work, we would like to explore whether the propagation speed, taking into account the propagation speed of the cascades, can help us in characterizing better the echo chambers. And these are my personal contacts, my email and my website, whether you are interested in contacting me. Thank you.